Introduction to Pseudo-random numbers. In this video, we are going to learn about pseudo-random numbers. True random number generators use measurements of a truly random event and are not widely used in computational experiments. Pseudo-random numbers are generated from a seed by the deterministic algorithm and are random in the sense that they pass statistical tests. Their means, variances, and distributions may be computed and agree with the underlying distribution to a higher degree of accuracy. Further, correlations between pairs of pseudo-random numbers may be computed and indicate that successive instances are uncorrelated to a high degree of accuracy. MATLAB and other scientific computing environments make pseudo-random number generators available. Pseudo-random numbers are random enough for most purposes, though user can certainly find non-random effects such as periodicity, whereby the sequence of random numbers is repeated after a large number of calls. Usage of pseudo-random numbers. Almost all network security protocols rely on the randomness of certain parameters. Nonce used to avoid replay. Session key. Unique parameters in digital signatures. Monte Carlo simulations. Monte Carlo simulations is a mathematical technique for numerically solving differential equations. Randomly generates scenarios for collecting statistics. Properties of pseudo-random numbers. Uncorrelated sequences, a long period, uniformity, efficiency. Uncorrelated sequences. The sequences of random numbers should be serially uncorrelated. Long period. The generator should be of long period. It is ideally the generator should not repeat. Practically, the repetition should occur only after the generation of a very large set of random numbers. Uniformity. The sequence of random numbers should be uniform and unbiased, that is, equal fractions of random numbers should fall into equal areas in space. Example, if random numbers on 0, 1 are to be generated, it would be a poor practice where more than half to fall into 0, 0.1, presuming the sample size is sufficiently large. Efficiency. The generator should be efficient. Low overhead for massive parallel computations. Random number cycle. Almost all random number generators have as their basis a sequence of pseudo-random integers. The integers or fixed point numbers are manipulated arithmetically to yield floating point or real numbers. The nature of the cycle. The sequence has a finite number of integers. The sequence gets traversed in a particular order. The sequence repeats if the period of the generator is exceeded. The integers need not be distinct, that is, it may repeat. Testing pseudo-random generators. Algorithms have been developed without failure which generate sequences of numbers which pass every statistical test used to distinguish random sequences from those containing some pattern or internal order. Tests to check the different properties of pseudo-random numbers discussed above. Tests include mean and variance checks. A mean should be close to 0.5 and variance 1 by 12, which is equal to 0.08 for uniformly distributed pseudo-random numbers. Theory of pseudo-random numbers. In this video, we are going to see about the theory of pseudo-random numbers. Theory of pseudo-random numbers. Computational indistinguishability considers an ensemble, that is a sequence of numbers. Now, if user can generate an ensemble which cannot be differentiated from the first ensemble in polynomial time by any efficient procedure, the second ensemble is, for all practical purposes, equivalent to the first ensemble. Ensembles that are computationally indistinguishable from a uniform ensemble are called pseudo-random. General definition of pseudo-random numbers: a deterministic polynomial time algorithm which satisfies the following two conditions: expansion, pseudo-randomness. Expansion. Expansion for every S, E of 0, 1 group, modulus of G of S is greater than modulus of S. Pseudo-randomness. The ensemble G of S is pseudo-random. Significance of pseudo-random generators: efficient amplifiers or expanders of randomness. Using very little randomness, that is a randomly chosen seed, they produce very long sequences which look random to any efficient observer. Pseudo-random generators allow to produce high-quality random sequences at low cost, making them very useful in cryptography. They produce unpredictable sequences, that is, no efficient algorithm can guess its next bit given a prefix of the sequence. Pseudo-random number generators. In this video, we are going to see about pseudo-random number generators. The first type of pseudo-generator is a random number generator, RNG. An RNG uses a non-deterministic source, that is the entropy source, along with some processing function, that is the entropy distillation process, to produce randomness. The use of a distillation process is needed to overcome any weakness in the entropy source that results in the production of non-random numbers, for example, the occurrence of long strings of zeros or ones. The entropy source typically consists of some physical quantities such as the noise in an electrical circuit, the timing of user processes, that is, for example, keystrokes or mouse movements, or the quantum effects in a semiconductor. Various combinations of these inputs may be used. The outputs of an RNG may be used directly as a random number or may be fed into a pseudo-random number generator, PRNG. To be used directly, that is, without further processing, the output of any RNG needs to satisfy strict randomness criteria as measured by statistical tests in order to determine that the physical sources of the RNG inputs appear random. For example, a physical source such as electronic noise may contain a superposition of regular structures such as waves or other periodic phenomena, which may appear to be random, yet are determined to be non-random using statistical tests. There are several generators for pseudo-random number. Some of them are linear congruential generators, R250, shuffling numbers, quasi-random numbers. Linear congruential generators. The most commonly used for generating random integers. xn plus 1 is equal to axn plus c mod m. xn is equal to nth random integer, xn plus 1 is equal to n plus 1th random integer, a is the integer multiplier, c is the integer additive constant, m is the modulus for modulo arithmetic. User can generate the next random integer using the previous random integer, integer constants, and the integer modulus. The sequence generated as the appearance of randomness is provided by performing modulo arithmetic or remaindering. Note that the next result depends upon only the previous integer. LCG of A, C, M, X0. This is a characteristic of linear congruential generators which minimizes storage requirements but at the same time imposes restrictions on the period. With Xn determined, user can generate a corresponding real number as follows. Rn is equal to xn by float m, or Rn is equal to xn by float m minus 1. When dividing by mRn, the values are then distributed on 0, 1. The user desires uniformity, where any particular Rn is just likely to appear as any other Rn and the average of the Rn is very close to 0.5. Example: LCG of 5, 1, 16, 1. Consider a simple example with A is equal to 5, C is equal to 1, M is equal to 16 and X0 is equal to 1. The sequence of pseudo-random integers generated by this algorithm is 1, 6, 15, 12, 13, 2, 11, 8, 9, 14, 7, 4, 5, 10, 3, 0, 1, 6, 15, 12, 13, 2, 11, 8, 9, 14 and so on. The period, that is the number of integers before the sequence repeats, P is 16, exactly equal to the modulus M. Thus, for M is equal to 16, this sequence is of long period, that is the longest possible, and uniform, that is it completely fills the space of integers from 0 to 15. Sequence exhibits throughout its period the pattern of alternating odd and even integers. It is readily apparent that the sequence is serially correlated. Due to this lack of randomness, the values should not be used as random digits. The real numbers generated from the integer sequence are generally sufficiently random in the higher order, that is, most significant bits, to be used in many application codes. Each random integer results from the previous integer alone. Selecting any initial seed from 0 to 15 would just cyclically shift the above sequence. Thus, all that a different choice of the initial seed does is shift the starting point in the sequence already determined by A, C, and M. Finally, note that the average of the real numbers is 0.4688 and the variance is 0.0830. The departure of these values from the ideal ones of 1 by 2 and 1 by 12 is due to the short period of this sequence and the rather coarse resolution of the generated real numbers. These conditions of average and variance approaching the theoretical values are necessary but not sufficient conditions for a good random number generator. When debugging, it is important to implement the algorithm to reproduce the same stream of random numbers on successive runs. The initial seed should be set to a random odd value, R250. R250 uses a shift register sequence. It has several advantages over a linear congruential generator. Long period 2 power 249. Period does not depend upon the number of bits used in the random number generator. Generally much faster than an LCM implementation. Generator is built from a 1-bit random generator based on the following equation. Ik is equal to C1 Ik minus 1 plus C2 Ik minus 2 plus and so on up to Cp minus 1 Ik minus P plus 1 plus Ik minus P plus 1 plus Ik minus P mod 2. The max period is 2 power P minus 1. User will use the value of P is equal to 250. Choosing most of the Ci terms to be 0, user get the equation Ik is equal to Ik minus Q plus Ik minus P. If user choose q is equal to 1 or 3, then the number generated is got by adding the previously calculated 103rd bit and the 250th bit. To generate a random number of 16 or 32 bits, this can be done by doing the above 1-bit addition for each bit in the desired random number. Since exclusive OR is the same as bitwise addition, all the bit operations can be done in parallel. This gives the speed advantage. Shuffling numbers. Shuffling numbers is desirable to randomize a small set of numbers so that a non-repeating sequence is obtained in some times. It is important not to repeat numbers. Taking the modulus of a generator like R250 will not work as the numbers could repeat. One way to do this would be to put the value to be shuffled into an array and to use a random number generator to generate indices into the array to actually shuffle the numbers. Quasi-random numbers. For some applications, pseudo-random numbers are a little too random. Some portions of the domain are relatively undersampled and other portions are oversampled. Quasi-random number generators maintain a uniform density of coverage over the entire domain by giving up serial independence of subsequently generated value in order to obtain a uniform coverage of the domain. Classes of attacks on pseudo-random number generators, PRNGs. In this video, we will learn about classes of attacks on pseudo-random number generators, PRNGs. There are three classes of attacks on pseudo-random number generators, PRNGs. Direct cryptanalytic attack, input-based attack, state compromise extension attacks. Direct cryptanalytic attack. Direct cryptanalytic attack is when the attacker can distinguish between the generator and random noise. This is the most basic type of attack, but often the most difficult since the statistical methods above can help prevent this kind of attack. Also, if the output of a PRNG is never directly seen by an attacker, this kind of attack cannot be used. Input-based attack. Input-based attacks are when the attacker manipulates the input of the PRNG to distinguish the output. If the input is easily predicted, then the state may also be predicted. Types of input-based attack: known input, chosen input, relayed input. Known input. If the inputs to the PRNG that are designed to be difficult for a user to guess turn out to be easily deductible, for example, disk latency time. When the user is accessing a network disk, the attacker can observe the latency time. Chosen input. Practical against smart cards, applications that feed incoming messages, that is username or password etc. to the PRNG as entropy samples. Relayed input. Similar to chosen input, except it requires less sophistication on the part of the attacker. State compromise extension attack. State compromise attacks are using revealed information to determine information about past or future states of the PRNG. If seeds are stored on a disk between uses, it could be used to get information about prior or future uses of the system. Alternatively, if the system uses a predictable seed, these methods could be used to gain information about the later outputs of the system. And also, it attempts to extend the advantages of a temporary security breach. These breaches can be inadvertent leak, previous cryptographic success. This attack is successful when the attacker learns the internal state of the system at state S, able to recover unknown PRNG outputs from before S was compromised. These attacks are classified as backtracking attacks, permanent compromise attacks, iterative guessing attacks, meet-in-the-middle attacks, tests for pseudo-random functions. In this video, we will learn about the tests for pseudo-random functions. Pseudo-random functions contains two tests such as quantitative test, qualitative test. Quantitative test, X-square test, measure how well the presumed distribution, that is usually uniform, is represented. Algorithm for the test. Divide the whole interval within which the random number would be into finite number of bins, that is class intervals. Assume they have same size. Count the number of random numbers within each interval and calculate the expected number of observations, that is, number of random numbers used divided by number of class intervals for uniform intervals. Calculate x square is equal to summation of I is equal to 1, m observed I minus expected I the whole square divided by expected I. The value of x square determines if the numbers generated represent a chosen distribution by looking up in a table some critical values of x square. Lagged correlation. This test reveals the relationship between the numbers at one time and at another, that is autocorrelation. Reveals trends and periodicity of numbers. Properties of an ideal random number generator. Autocorrelation value is equal to 1 for lag of tau is equal to 0. Autocorrelation value is equal to 0 for any other value of tau. If the autocorrelation values slowly drop to 0 as tau increases, then the random numbers generated are not very independent of each other. Qualitative test. Scatter plots. Scatter plots are similar to line graphs in that they use horizontal and vertical axes to plot data points. Random walk. Algorithm. Divide the range of the random number generator into equal intervals. Divide into 4 intervals for a random walk in 2 dimensions. Generate a number if the number falls in first interval, increment x. Second interval, increment y. Third interval, decrement x. Fourth interval, decrement y. Generate t steps for a random walk for n walks. Calculate the mean squared distance reached. Plot this distance against time. A plot for several values of t and distance should roughly be linear, else the random numbers are not correctly distributed. Truly random numbers. In this video, we will learn about truly random numbers. True random numbers are typically generated by sampling and processing a source of entropy outside the computer. A source of entropy can be very simple, like the little variations in somebody's mouse movements or in the amount of time between keystrokes. Keystrokes, for example, are often buffered by the computer's operating system, meaning that several keystrokes are collected before they are sent to the program waiting for them. To the program, it will seem as though the keys were pressed almost simultaneously. Must rely on external physical quantities. Computers require special hardware. Few computers have access to this kind of hardware. Example, sensors, that is heat or pressure, etc. Randomness without relying on external data. Some way to measure internal activity of the computers such that the activity is quantifiable and genuinely random. Example, timing of keystroke. Some physical quantities used in real world for true random number generation. Timing of keystrokes when a user enters a password. measurement of air turbulence due to the movement of hard drive heads. Measurement of timing skew between two system timers such as a hardware timer, a software timer. Finally, examined that random numbers are the basis for many cryptographic applications. There is no reliable independent function to generate random numbers. Present-day computers can only approximate random numbers using pseudo-random numbers generated by pseudo-random number generators (PRNGs). Attacks on many cryptographic applications are possible by attacks on PRNGs. Computer applications are increasingly turning towards using physical data, that is external or internal, for getting truly random numbers. Next bit test. In this video, we are going to learn about next bit test. Any witness algorithm applies a statistical test. As a witness algorithm has to run in polynomial time, the statistical test used in the witness algorithm has to be polynomial. The statement, a bit generator is pseudo-random, can be equivalently rephrased as a bit generator passes all polynomial time, that is statistical tests. Among all polynomial time tests, one can define the subclass of next bit test. Given a bit generator which produces n power I bit sequences. Let T be a probabilistic polynomial time test that takes first I bits of an n power I bit output sequence and guesses the I plus 1th bit. The bit generator passes the next bit test if for any probabilistic polynomial time test T, for all polynomials gamma of n, for all sufficiently large n, and for all integers I belongs to 1 and so on up to n power I. Modulus of P of Tn of b1 and so on up to bi is equal to bi plus 1 minus 1 by 2 is less than 1 by gamma of n, where Tn of b1 and so on up to bi is equal to bi plus 1 is the probability that the correctly guesses the I plus 1th of the output sequence b1 and so on up to bn power l. The importance of next bit test is confirmed by the following theorem. Given a bit generator, there the following two statements are equivalent. The bit generator passes the next bit test. The bit generator passes all probabilistic polynomial time statistical tests for output sequences. Blam and Micali defined cryptographically strong pseudo-random hit generators as bit generators that pass the next bit test. The two notions, cryptographically strong pseudo-random bit generators and pseudo-random bit generators (PBG), are equivalent. The next bit test is universal in the sense that if a PBG passes the next bit test, it also passes all other probabilistic polynomial time tests. Removing biases. In this video, we are going to see about removing biases. Bias refers to giving a preference to one group over another. Removing bias is possible from a stream of random numbers. The three popular methods of removing bias are the von Neumann, exclusive OR, hashing. The von Neumann. Take two independent 1-bit samples. If the bits are the same, discard them and take two more. If they are different, use one of the bits as the output. This method has the nice property that it's theoretically perfect. Regardless of how biased the original source is, the output is exactly as likely to be a 1 or a 0. Exclusive OR. Exclusive OR, that is XOR, involves taking a chunk of the stream and reducing the number of bits by XORing them together. XORing enough bits brings the probability of a 1 close enough to 50% for all practical purposes. This is guaranteed to produce numbers in a known amount of time, but it uses up a lot of bits. Hashing. Hashing involves running a chunk of bits through a hashing function. CRC16 only takes about 6 bits to equal the performance of 10 XORed bits, and larger hashing functions work better. User can feed almost anything into a hashing function and distill it down to just the randomness. SHE1 and MD5 are popular hashing functions in cryptographic random number generators like Y-arrow. SHA1 is used mostly for security reasons, not because it produces a higher quality of random number. However, it does do a better job of mixing than CRC does. ANSI X 9.17 generator. In this video, we are going to see about ANSI X 9.17 generator. Algorithm for ANSI X 9.17 pseudo-random bit generator. Input: a random and secret 64-bit seed S, integer M, and DES EDE encryption key K. Output: M pseudo-random 64-bit strings x1, x2 and so on up to xm. Compute the intermediate value I is equal to ek of d, where d is a 64-bit representation of the date or time to as fine a resolution as is available. For I from 1 to m, do the following. xi is equivalent to ek of I XOR with s. S is equivalent to ek of xi is XOR with I. Return x1, x2 and so on up to xm. This algorithm is a US Federal Information Processing Standard FIPS approved method from the ANSI X 9.17 standard for the purpose of pseudo-randomly generating keys and initialization vectors for use with DES, that is Data Encryption Standard. EK denotes DES EDE 2-key triple encryption under a key K. The key K should be reserved exclusively for use in this algorithm. Each output bit string xi may be used as an initialization vector IV for one of the DES modes of operation. To obtain a DES key from xi, every 8th bit of xi should be reset to odd parity. Blam sub generator. In this video, we are going to see about blam sub generator. Generating secure pseudo-random numbers is known as the blam sub generator, BBS. It is a popular approach named for its developers, Blam86. It has perhaps the strongest public proof of its cryptographic strength of any purpose-built algorithm. The procedure is as follows. First, choose two large prime numbers p and q that both have a remainder of 3 when divided by 4. P is equal to q is equal to 3 mod 4. This notation simply means that p mod 4 is equal to q mod 4 is equal to 3. Example: the prime numbers 7 and 11 satisfy 7 is equal to 11 is equal to 3 mod 4. Let n is equal to p into q. Next, choose a random number s such that s is relatively prime to n. This is equivalent to saying that neither p nor q is a factor of s. Then the BBS generator produces a sequence of bits bi according to the following algorithm. x0 is equal to s square mod n. For I is equal to 1 to infinity, xi is equal to xi minus 1 the whole square mod n. Bi is equal to xi mod 2. Thus, the least significant bit is taken at each iteration. Following table shows an example of BBS operation. Here, n is equal to 1,92,649 is equal to 383 into 503 and the seed S is equal to 1,01,355. The BBS is referred to as a cryptographically secure pseudo-random bit generator CSPRBG. A CSPRBG is defined as one that passes the next bit test, which in turn is defined as follows. A pseudo-random bit generator is said to pass the next bit test if there is not a polynomial time algorithm that, on input of the first k bits of an output sequence, can predict k plus 1 bit with probabilities significantly greater than 1 by 2. In other words, given the first k bits of the sequence, there is not a practical algorithm that can even allow user to state that the next bit will be 1 or 0 with probability greater than 1 by 2. For all practical purposes, the sequence is unpredictable. The security of BBS is based on the difficulty of factoring n. That is, given n, user need to determine its two prime factors p and q. Statistical test. In this video, we are going to see about statistical test. In order to distinguish randomness from non-randomness, user need to use a statistical test. An example of such a test might be to check that approximately a half of the bits in a given string are 0. It is easy to come up with a long list of possible statistical tests which user could use to check a bit generator for pseudo-randomness, but user can never be sure that outlist is exhaustive. If user base the randomness of their pseudo-random generator on a predetermined list of tests, they run risk that an adversary may develop a new test which can somewhat distinguish the output of our pseudo-random generator from a random source. This would be problematic, so they demand that a pseudo-random generator should be able to pass any reasonable statistical test. The normal and chi-square distributions. The normal and chi-square distributions are widely used in statistical applications. If the result chi of an experiment can be any real number, then chi is said to be a continuous random variable. A probability density function of a continuous random variable chi is a function f of x which can be integrated and satisfies f of x is greater than or equal to 0 for all x belongs to R. Integrate minus infinity to plus infinity, f of x dx is equal to 1, and for all a, b belongs to R, p of a less than chi less than or equal to b is equal to integral a to b f of x dx. A continuous random variable chi has a normal with a mean mu and variance sigma square if its probability density function is defined by f of x is equal to 1 by sigma square root of 2 pi axp minus of x minus mu square divided by 2 sigma square, ranges from minus infinity less than x less than plus infinity. Notation: chi is said to be n of mu comma sigma square. If chi is n of 0, 1, then chi is said to have standard normal distribution. The normal distribution arises in practice when a large number of independent random variables having the same mean and variance are summed. A graph of the n of 0, 1 distribution. The graph is symmetric about the vertical axis, and hence p of x greater than x is equal to p of x is less than minus x for any x. The following table gives some percentiles for the standard normal distribution. For example, the entry alpha is equal to 0.05, x is equal to 1.6449 means that if x is n of 0, 1, then x exceeds 1.6449 about 5% of time. Table shown selected percentiles of the standard normal distribution. If x is a random variable having a standard normal distribution, then p of x greater than x is equal to alpha. Notation: if the random variable x is n of mu, sigma square, then the random variable z is equal to x minus mu the whole divided by sigma is n of 0, 1. Let v is greater than or equal to 1 be an integer. A continuous random variable x has a chi-square distribution with new degrees of freedom if its probability density function is defined by f of x is equal to 0 to gamma 1 by nu by 2 into 2 power nu by 2 into x power nu by 2 minus 1 into e power minus x by 2, where 0 is less than or equal to x less than infinity, x is less than 0. Where gamma is a gamma function. The mean and variance of this distribution are mu is equal to nu and sigma squared is equal to 2 nu. The chi-square distribution can be used to compare the goodness of fit of the observed frequencies of events to their expected frequencies under a hypothesized distribution. The chi-square with new degrees of freedom arises in practice when the squares of new independent random variables having standard normal distributions are summed. The graph of the chi-square distribution with nu is equal to 7 degrees of freedom is given. The following table shows some percentiles of the chi-square distribution for various degrees of freedom. For example, the entry in row nu is equal to 5 and column alpha is equal to 0.05 is x is equal to 11.0705. This means that if x has a chi-square distribution with 5 degrees of freedom, then x exceeds 11.0705 about 5% of the time. Selected percentiles of the chi-square distribution, a v, alpha entry of x in the table has the following meaning. If x is a random variable having a chi-square distribution with new degrees of freedom, then p of x is greater than x is equal to alpha. Notation: if the random variable x is n of mu, sigma square greater than 0, then the random variable z is equal to x minus mu square into 2 divided by sigma square has a chi-square distribution with 1 degree of freedom. In particular, if x is n of 0, 1, then z is equal to x square has a chi-square distribution with 1 degree of freedom.